Hello, welcome back to ECE484, fall 2021. We are into our home stretch here, so let's keep going. Okay, so we have been talking in this chapter, chapter 7, about discretizing plants to get a discrete time plant to be able to do design in the discrete time domain. Okay, the basic idea is that we take our standard sample data system, where we have the continuous time plant and the computer where the controller resides, and we just kind of shift our point of view a little bit and we put the sampler at the output of the plant. Don't change the diagram, just move some blocks around. Okay, so no approximations, no changes made, just moving blocks around. Okay, and then we're going to basically take this box here, this purple box, and we're going to design controllers for the system in that purple box. And so in this chapter we wanted to learn how to compute that purple box. That is the step invariant transformation of a continuous time plant. Okay, and we started with state space approach to this. In other words, where the continuous time plant has a state space model. And we went through the details of how you would go about computing that. And what we ended up with was a discrete time state space model like this, where essentially it has the same structure, of course, but the A and the B matrices have changed, right? Instead of A and B, which we started with, we now have A sub D for a discretized A matrix, and B sub D for discretized B matrix, which are computed by these formulas here, and we derive these formulas. Okay, so we did some examples of these calculations, all right? And so you should feel comfortable doing that. And then we studied what properties of this system sort of are reflected in this system. In particular, we looked at the eigenvalues. Why did we care about the eigenvalues? They very much tell us about stability, right? They directly tell us about asymptotic stability, as well as input-output stability, so Bibo stability. Okay, and what we showed was that if you have an eigenvalue lambda of the original A matrix, you can think of that as a pole of P of S, then you just take that eigenvalue, multiply it by capital T, the sampling period, and then exponentiate, and that number, in general complex, is an eigenvalue of the discretized system. So an eigenvalue of AD, or if you prefer, a pole of the discretized plant transfer function. And we showed that, and then of course from that it follows why the step invariant transformation preserves stability, right? So if the continuous time system is stable, the discretization will be stable, and vice versa. If the discretization was stable, or is stable, then it must have been produced by a stable, well, in most cases, stable continuous time system. Okay, and we'll see more about that today as well. Okay, so that's where we left off, and then we started looking at, I'm going to just scroll down here, this. So this is essentially what we did last class, going from a continuous time model to a discrete time model. This is stuff we have done previously, right? Going from a state space model to a transfer function. And what we started looking at is there a way to go from a continuous time transfer function model to a discrete time transfer function model directly, right? Without having to do this path along the top, okay? And so that's where we left off, right? So here we have our continuous time plant with a hole in a sample around it, and we want to be able to compute the discretization. Okay, we're going to continue from there. So the first observation we're going to make is basically that what we're going to do here is we're going to say, look, this is a linear time invariant system. It's LTI. So the ratio of the Z transform of the input to the Z transform of the output is going to be the same no matter which input-output pair we pick. So that's the first observation. This is an LTI system. So the ratio of the Z transform of the output over the Z transform of the input is the same for any input-output pair. And so we just pick a convenient input U, compute the resulting response of the system, sample it, take the z transform of it, and then that will get our transfer function. And so what would be a convenient choice for you? Well, we could try the discrete impulse, but that would be a bit messy because it would work, of course, as I mentioned, any input-output pair would work. But this, if we chose an impulse here for u, what we're going to get coming out, what we're going to get coming out over here is going to look something like this. It's going to be a pulse at this point up here. And that's going to have a delay in it. It's going to be messy. So it's just easier to take this guy to be the step, unit step, because then this signal will also be the continuous time unit step. And that is just a convenient choice. Any input-output pair will work, but let's just pick a convenient one. Use the step. Okay, so here's our procedure. I'm going to pick the step input for the reasons I just discussed for u. So okay, take u of k equal to 1 of k, then the z transform of that guy is this. I make note of that here because remember at the end, whatever we get for the output y, I want to divide by u. And so I'm going to have to divide by this transform at the end to get my transfer function. So there's my input. 2, the hold of u of k is equal to the continuous time step. Okay, and so and the Laplace transform of the step is 1 over s. Okay. 3, the output of the plant, the continuous time plant, in other words, this here, we just applied a step here, we got a continuous time step here, and so the output over here on this side, the output of the plant, continuous time plant, is going to be the unit step response of the continuous time system. And so we will get that y of s equals p of s times 1 over s, right? Unit step response. Take the Laplace inverse of that because we're going to have to sample. So we'll say that y of t is the Laplace inverse of that response. Okay? Step 4, sample the resulting step response. Right? So sample y of t. To get okay. I don't have a concrete expression for y of t, I just have that Laplace inverse. So let's write this as I take that Laplace inverse and I evaluate it at t equal to kt. Okay, so now we have y of k. We can get y of z from it. So y of z is the z transform of y of k, which is that expression from step 4. And we get the transfer function. Right, the ratio of those two transforms. And if we just unfurl or unwrap all the various steps here, we get the following. This equals, okay, so I'll divide by the u of z. So u of z is z over z minus 1. So when I divide, we get a reciprocal So we will get here z minus 1 over z. Okay, so that's 1 over u times y of z. And y of z is listed above, so let's just write it out. It's going to be the z transform of the Laplace inverse of p of s times 1 over s, where we've sampled that step response. Okay, and that's our formula. It looks messy, but conceptually, it should be clear what we're doing here. Okay, we are just basically stepping through the block diagram and doing steps, taking Laplace and z transforms as needed. Okay, so this is how you would compute the discretized transfer function directly from the continuous time transfer function. Now, of course, this is going to be tedious for high-order plants or multi-input systems, for example, multi-input, multi-output systems. There you'd really want to do state space. MATLAB, of course, does it in state space calculations. But for small problems, this is a pretty simple method. Okay, so we're going to do an example now to illustrate it. So let's do an example, like I said. And so let's return to an example we did last class. Last class, we found we did the state space approach to discretizing a first order system. So now let's do the transform approach and see that we get the same answer. And so the plant, the continuous time plant, is this guy, okay? And this was the system from example 7.2.3, which we did last class, okay? So same continuous time system, we're just going to do it in the transform approach. Okay, so we want to find C to D. Right, the step invariant transform of that plant. And we just need to go through the steps. So if we look at the box formula above, the first thing we're going to need is the continuous time step response. I need the continuous time step response of this plant in order to sample it and then take its Z transform. So we have P of S times 1 over S. That's to generate the step response. In this case, is given by if you do a partial fraction expansion on this, you will get first order step response. We know what that looks like, so this one's actually very easy to compute. So there's our P of S. That's the step response in the Laplace domain. We want to go to the time domain, so we get from that going back to the time domain, right, Laplace inverse of that expression, sample, what does sampling mean? Everywhere you see the time variable, replace it with k, the discrete time index, times the sampling period. So I'm going to write this as negative 2t to the power of k. Or times k, sorry. K greater than or equal to 0. Take the Z transform of this. So the first part looks like a step, so we're going to get 1.5. In fact, let's keep that 1.5 factored out outside. So Z minus 1 minus, this is a familiar Z transform, right? We did the Z transform of some number to the power of k. That's what we have here. So this is simply that expression. Okay, and finally, to get the transfer function, we need to divide the z transform of the output by the z transform of the input. Because of this step here, remember, we've taken the discrete time input to be the step. That's why the continuous time input is a step as well. Okay, so finally, right, we just have to take the expression y of z above, multiply it times, or divide it, if you want to think of it this way, by z over z minus 1. And you will get the same answer we got before. Okay, and this is our final answer. I'll just point out that this is the same expression as what we had in example 7.2.3. Okay. Now, for first order systems, to do by hand, very simple, right? Whether you want to do it in the state space method or the Laplace method, either of them is quite easy to do by hand. As you get to bigger problems, the state space approach, or multi-input systems, the state space approach scales better and it's easier to do on a computer. Okay, so we've now basically finished our discussion on how do you discretize a plane, how do you compute the step invariant transformation. And so a couple of questions to ponder. If I have two continuous time systems in parallel, and I try to discretize them, what does the discretization look like? So the question can be phrased this way. If I have two transfer functions, P1, right, so this, you can think of this as a parallel connection. Does that equal the parallel connection of the discretizations? You can think about this yourself, but the easiest way to answer that is the answer is yes, is just draw the block diagram. Draw the block diagram and see what, and convince yourself that this is true. So the answer is yes. Okay, what about the series connection of two systems? So this would be like a series connection. And then the question is, does this equal the series connection of the discretizations? Okay, and the answer is no, and there's an example in the notes illustrating this. So the answer is no. I guess it's an exercise, but see exercise 7.5 in the notes. Okay. All right. So we now know how to compute the step invariant transformation. We know some properties really of eigenvalues and poles between the continuous time model and the discretization. Let's study a few more effects of sampling. So I want to talk a little bit more about the effects and let me just copy the block diagram of our closed loop system from above. I'm going to paste it here. Give me a second. So let's copy that. didn't work. Okay. So this is our system, right? And we said that what we've done now, we're in a position to basically treat the continuous time plant like a discrete time plant and just do our design. And the important point is that there are no approximations in this diagram. So let's, again, I've written this before. The above system where, of course, this is P sub D. The above system has no approximations. What we're doing is in reality here is we're just looking at the evolution of the sample data system, but we're only looking at the sample periods. We are ignoring the behavior between the samples. Of the sample data system only at the sample instances. Right? There is stuff happening between the samples because there's this continuous time element, but this model won't capture that in some sense. Right? It's just going to be a discrete, it'll look like a discrete time system. And so the natural question is, if we're only looking at the behavior of the sample points, can we be sure that the continuous time plant, which is at the end of the day the thing you're controlling, can we be sure that just looking at the sample instances, things are working out as expected? So can we, for example, can we deduce say stability of the closed loop system? Sample data system. Right, which is sample data, a mixture of continuous and discrete, by examining the behavior at only the sample instances. Right? In other words, we're going to treat it like a discrete time system. Is that going to cause any issues for our design and analysis? Okay? And so the answer to that is yes, in most cases. But not always. Okay, I'm going to do an example, right? So basically, in practice, in almost all real cases, it's not going to be an issue, but we have to be a little bit careful, and that's what I want to talk about here. So pathological sampling, meaning in the sense that it's sort of very rare, or it's kind of very odd. But let's see what can happen. So suppose you have a plant whose transfer function looks like this. Okay, I'm using omega s because that's eventually going to be the sampling frequency. Okay, so this is a plant, which is an oscillator. With natural frequency omega s. Okay, and if you look at its poles, it has two poles on the imaginary axis at plus or minus omega s. It also has a 0. Okay, so this is the real part of S. Okay, so suppose the design problem here is stabilize this system. It's open loop unstable, right? The only specification is stability. It's open loop unstable, so we have to do something. We can't just let it stick around. So we're gonna design a just digital controller to stabilize this plant. And suppose we make the unfortunate decision to sample at the same frequency omega s. So suppose we discretize at a sampling rate, frequency, let's say, of omega s, which is 2 pi t. Right, so we've chosen our sampling period t to be exactly equal to this omega s from the plant model. Okay, we just figured out how to compute c to d of a plant. Let's apply that technique here. So compute c to d. Okay, remember from our last example, what do we have to do? We have to first find the continuous time unit step response, sample that, etc., etc. So step response so this would be P of S times 1 over S. So let's multiply that out. All right, so same thing we just finished doing. The S's are going to cancel there in that expression. And so this signal that we get, as you can see, it's going to be just, let's cancel this out. It looks like the Laplace transform of a sinusoid. Indeed, it is. Okay, so there's our step response. And if we want to find the discretized plant, well, we have to sample that signal and then take its Z transform. So if we sample now, so what do? We take the continuous time system, because the step response, continuous time step response, and we replace the time variable with k times the sampling frequency, or sampling period. Okay, so in this case, it's going to be sine of omega s. I'm going to write omega s in terms of the sampling period, times kt. Okay. These guys will cancel out. And we have sine of 2 pi k. Which is exactly 0 for all k. Okay. So now we have a discrete time signal 0. Of course, when we take its Z transform, that's going to be 0. And then we divide by Z over Z minus 1, we still have 0. So the discretized plant that we get here is the 0 plant. Okay, well, then our problem is solved, right? The only specification we had was to stabilize this plant. The discrete time plant is stable already. Trivial, right? Bounded input, bounded output stable. Nothing to do. Wash our hands and walk away. Of course, there's a problem, right? The problem is that because we're only examining the sample periods, we're not capturing the intersample behavior, the fact that the system is actually unstable, right? The underlying continuous time system is unstable. So what happened here? Okay, well, we'll go back and see what happens, but let's point out, if the original plant was 0, also yields C to D being equal to 0. So in other words, this function, this discretization function, it's not one-to-one. You can take two different plants in continuous time when you discretize them and get the same plant in continuous time, in discrete time. And this is clearly a problem in this little example here, because our problem was to stabilize the plant. And when we discretize, it's not clear that there actually is a problem, right? We say, oh, well, it looks stable to me. So this is clearly a problem. For control design. And we'd like to avoid such situations. Okay, so what we'll do now is we'll see kind of how such situations arise, and also how we can be careful choosing our sampling period so that this doesn't happen, right? So this is yet another way to think about choosing our sampling period. Okay, so the scenario in that example is called pathological sampling. And we basically want to avoid this type of sampling. Okay? We're going to say that a sampling frequency is pathological relative to a continuous time plant, right? Whether or not a sampling period is pathological depends on the plant, the continuous time plant. So it's pathological relative to you can talk about a continuous time model, state space model, or you can talk about its transfer function. Either way, so pathological relative to a continuous time system. If two different eigenvalues of A or poles of P of S get mapped to the same eigenvalue or pole of the discretized system. All right, so that we want to avoid such sampling periods. So how do we characterize such a sampling frequency or sampling period? Well, it's a fact which you can check yourself, and this is exercise 7.8. two eigenvalues, we know how they get mapped, right? Eigenvalues of A get mapped to eigenvalues of AD through this exponential. We saw this last class. And so what we want to avoid for pathological sampling is that two different lambda 1 and lambda 2 eigenvalues of A don't result in the same discrete time eigenvalue. And this can happen, this is true, this can only happen if the difference between the eigenvalues is purely imaginary and an integer multiple of the sampling frequency. So let me draw a picture of this, right? So if you have two different eigenvalues of A, lambda 1, lambda 2, so they're distinct, right? If it's the same eigenvalue, it's fine. You would make sense if they get mapped to the same value. But if they're different, so lambda 1 is not equal to lambda 2, but then after you discretize them, they become the same, we're calling that pathological. And that can only happen if the difference between the eigenvalues, or the poles, is purely imaginary and is an integer multiple of the sampling frequency. So the picture would be something like this. Right, in the S-plane, you might have poles something like this. So say pole here, and pole here. And so what this is saying is that, these are clearly different locations in the S-plane, different poles or different eigenvalues. What we're saying is that if this distance, if you choose your sampling period, so that distance is omega s, where that distance is omega s, then they will get mapped to the same location after discretization, and you will lose basically some information about your plant. Okay, so the point here is we want to avoid pathological sampling because it can result in behavior of the sample data system which is not captured by the discretization. You can almost think of it as aliasing, but at a system level, not at a signal level, right? It's like aliasing of systems. Okay. Okay, so we want to avoid this type of situation. And so we'll do an example basically on how you compute these pathological sampling frequencies. So example 751. So suppose that you have a system, a continuous time system, and the eigenvalues of A are given by, let me write this down, 0, 0, plus or minus j, right? So those are our eigenvalues. We want to characterize or find all of the pathological sampling frequencies. for this system. Okay, that's what we'd like to do in this example. And so remember, for us, pathological sampling will occur if we pick the sampling frequency such that this relationship holds between eigenvalues of A. Okay, so let's start by drawing the eigenvalues of A and see where it's possible to get this sort of relationship to hold. Okay, so the eigenvalues of A, let's draw them. We have 2 at 0. Kind of draw them that way, sorry. And then a couple at j, plus and minus j. And then we also have one at 1 plus j times 2, and 1 minus j times 2. I guess this should be here. So again, back to our condition here, we're looking for eigenvalues or poles that have the same real part. In other words, the difference between them is purely imaginary. And so this looks like, on a picture like this, it looks like poles that are lined up vertically. Okay, and so let's group them into 2 groups. We'll call this group 1. Right? So there we see that the difference between those poles is purely imaginary, and so if we choose the sampling frequency poorly, we can make it so that the distance between those poles is an integer multiple of the sampling frequency. Okay, and same thing over here. Call this group 2. Same thing, right? These guys, these poles, the only thing that differs between them, the difference between them is purely imaginary. And so it's possible to satisfy that condition from above. Okay, so I already wrote it, I just drew the picture, but let me write that down. So we look for groups of eigenvalues with the same real part. Right? Visually, they're going to look like on a vertical line in the S-plane. Okay, and so as I wrote there, we have group 1. And group 2. Okay, so how can we satisfy the condition for, let's think about the case of group 1. So in group 1, if lambda 1 and lambda 2 are taken from group 1, then the condition, right, the condition is that the difference between these poles or eigenvalues has to be equal to j omega sk, can be satisfied, or is satisfied, if what? Well, let's look at the picture here. This distance here is 1. So if k times omega s equals 1, then this guy and this guy, that'll capture that difference. Right? There's also this distance between those 2 poles, 2. So if k times omega s equals 2, we'll again satisfy that condition for valid choices of lambda 1 and lambda 2. So we can choose that, we can have that condition be satisfied if omega s equals, let's just write it out. So the first ones we said, let's think about the case when we want the distance to be equal to 1. Well, 1 works. Half works, right? Take k equal to 2, we get 1. Omega s times 2, in this case, would equal 1. 1 over 3 works as well. 1 over 4, etc., etc. Right? For each of those, we just pick k equal to the denominator, and we can make omega s times k equal to 1. The other group, the other possibility, sorry, was that omega s times k is equal to 2. So 2 works. 1 works as well. Take k equal to 2. 2/3 works. Take k equal to 3, and so on. All right? So those are all the pathological sampling frequencies associated with this group. Okay. Now there's some redundancy here, right? You see that 1 shows up here, it also shows up here. So in fact, this set over here contains all of these as subset. So this just equals two over k, k greater or equal to 1. So in other words, if we choose omega s from that set, then this condition can be satisfied for a particular choice of k. All right, let's do the second group. Then lambda 1 minus lambda 2 equal to j omega sk is satisfied for some k if what? Well, let's look at over here. We want that omega s times k equal the distance between these two poles. So that distance is 4. So we need that omega s times k equal to 4. So in other words, omega s should be 4 divided by some integer. So in other words, we get again omega s equal to 4, 4 over 2, 4 over 3, 4 over 4, 4 over 5, etc., which is just equal to 4 over k. So that's the second collection of pathological sampling frequencies, resulting from the second group. Combine these two sets of frequencies, and you get all the pathological sampling frequencies. So the complete set is the ones from the first group in combination with the ones from the second group. Okay, but again, you see there's some redundancies, right? Like, for example, let's see, 1/2 shows up in this group. And you can see that eventually it's also going to show up in this group, right? 4 over 8, right? So because 2 divides 4, this is just all right. So what is it? So those are all the pathological sampling frequencies, and we've talked about avoiding them, right? So in this case, for this example, we should pick omega s greater than 4, so that we don't have any issues with pathological sampling. To avoid pathological. And so again, it's unlikely to occur, right? I mean, it's have to be very unlucky in some sense to get this pathological sampling, hence the name pathological, but it's still an issue, right? We want to make sure that we sample, if we have, you know, high frequency modes in our plant model, then, you know, or in other words, poles with a large imaginary part, then this is going to put a constraint, in some sense, on their sampling frequency. Okay, I've run out of time. I'll stop there, and we'll continue tomorrow. I'll stick around for a minute, but otherwise I will see you tomorrow.